The understanding of gravity that Newton had was sufficient to permit us to fly from the Earth to the Moon. Ever find yourself lost in the ebb and flow of time, wondering whether our understanding is only a small portion of the temporal iceberg? On its head, this revelation is not just a theory. It is said to be a key that could open the doors to the universe's mysteries, revealing a cosmos more intricate and inspiring than we could have ever imagined. How does the brand new theory of Brian Cox work? Does it rethink our conventional understanding of time? What are the possibilities and implications for how we perceive reality? Come along with us on an intriguing exploration throughout the history of the world itself as we examine Brian Cox's recently revealed groundbreaking theory pertaining to the nature of time. Vast mysteries await us in the universe around us, waiting to be discovered. Some of these mysteries involve puzzling aspects of both time and gravity, two crucial parts of our lives. Envision a world where time behaves strangely, where it can either alter the speed of forces or slow them down. Such ideas might not just keep us grounded, they lead us directly into the realm of Einstein's theories of relativity, where our understanding of time and gravity takes a peculiar turn. Albert Einstein, a well-known figure, provided us with a fresh perspective on the universe through his groundbreaking theories. His work laid the foundation for comprehending the behavior of time under diverse circumstances, particularly when traveling at extremely high speeds. It all began at the start of the 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The publication of special relativity in 1905 revolutionized our comprehension of space and time. Simply put, it demonstrates that the laws of physics remain the same for all observers, regardless of their motion, so long as they are not accelerating. This theory introduces the concept of relativistic effects, such as the well-known idea that time can speed up or slow down under certain circumstances. A fascinating thought experiment used to explain time dilation is the light clock. Imagine being in a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors parallel to the direction of movement. According to the laws of physics, the speed of light is constant for every observer. This means the light beam must appear to follow an extended diagonal path to an observer outside the spaceship. Since the path is longer for the outside observer, it would appear to take longer for the light to complete its journey. This apparent time difference between the two observers is what Einstein referred to as time dilation. For the observer in motion, time slows down relative to an observer at rest. Understanding how things change when moving at high speeds, known as relativistic effects, is more than just an abstract concept. Researchers use massive machines called particle accelerators, such as the Large Hadron Collider, to accelerate particles to nearly the speed of light. At such speeds, time must be considered differently to ensure accurate measurements. Einstein's special theory of relativity challenges our intuitive understanding of motion and time. It states that the rules of physics are the same for all observers, regardless of their motion. This contradicts everyday experience, where we expect that adding speed to an object simply makes it move faster. However, Einstein's theory establishes a universal speed limit. Nothing can travel faster than the speed of light. This leads to counterintuitive results. Events that appear simultaneous to one observer might not seem simultaneous to another moving at near light speed. Another consequence of special relativity is length contraction. This means that if an object is moving fast, it appears shorter in the direction of its motion when viewed from a stationary perspective. Then, there is Einstein's famous equation, equals mc squared. This formula reveals that energy and mass are interchangeable, a fundamental principle in understanding both high-energy physics and real-world phenomena like nuclear reactions. Special relativity isn't just a theoretical concept, it has real-world applications. For example, GPS technology relies on it. GPS satellites move at high speeds, and their clocks experience time dilation. If this effect weren't accounted for, GPS navigation would be significantly inaccurate. Thus, special relativity teaches us that time isn't absolute. It depends on motion. This challenges our conventional understanding of space and time, revealing that our everyday intuition about the universe may be flawed. But there's more. Enter Einstein's general theory of relativity, proposed in 1915. This theory delves deep into the relationship between gravity and spacetime. The prevailing belief before Einstein was that gravity was simply a force that pulled objects toward one another. However, Einstein proposed that gravity occurs because of the curvature of spacetime. Instead of viewing gravity as a mysterious force, it is better understood as the natural movement of objects through curved spacetime. Imagine spacetime as a massive, stretchy fabric. When a heavy object like a planet or star is placed on it, it creates a dent, just like how a heavy ball would distort a trampoline. Smaller objects moving nearby naturally follow the curves of this distortion. This explains why planets orbit the Sun, not because they are being pulled by an invisible force, but because they are moving along curved spacetime. General relativity provides an elegant explanation for planetary motion and predicts phenomena such as black holes, gravitational lensing, and even the expansion of the universe. This theory, distinct from the Newtonian concept of gravity, has been confirmed by multiple experiments, including the observation of light bending around massive celestial bodies and the precise tracking of planetary orbits. Brian Cox's exploration of time and gravity continues to build on these ideas, pushing the boundaries of our understanding. What new discoveries await us? The universe is full of mysteries, some of which might redefine our very perception of time itself. The general accuracy of relativity was demonstrated during a solar eclipse in 1919. Sir Arthur Eddington led a group to observe how light from distant stars was bent by the sun's gravity. As the star's light passed near the sun, it shifted in accordance with Einstein's theory. The starlight would also dim due to the sun's mass. During the eclipse, the light curved slightly, confirming Einstein's predictions and demonstrating the validity of the theory. Just as motion can change how we experience time, general relativity also shows that gravity impacts time. In regions where gravity is particularly strong, time moves more slowly compared to areas with weaker gravity. If you were standing close to a massive object, such as a black hole, your clock would run slower than one positioned farther away from this powerful mass. General relativity also introduced the concept of black holes, regions where gravity is so intense that nothing, not even light, can escape. The edge surrounding a black hole is known as the event horizon, a point beyond which there is no return. If anything crosses this boundary, it gets pulled into the black hole with no chance of escaping. Einstein's theory of general relativity has significant implications for the structure of the universe. Initially, he added a cosmological constant to his equations, believing the universe was static. However, when it was discovered that the universe is expanding, he referred to this as a major error. The concept of an expanding universe, in accordance with general relativity, is a key part of the Big Bang theory, which describes how the universe began. Another important idea from general relativity is gravitational waves. These are ripples in the fabric of space and time caused by extremely massive objects moving rapidly, such as merging black holes or neutron stars. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, demonstrating yet another aspect of Einstein's theory. Scientists have conducted numerous tests to determine whether relativity is accurate, and each time, the theory has been validated. Observations of planetary motion, the bending of light from stars, and gravitational waves all confirm general relativity as a robust and reliable theory. While it might seem surprising to question gravity, especially since we experience it daily, physicists frequently investigate and challenge established scientific concepts. One alternative idea is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at slow speeds, particularly in galaxies, without requiring dark matter. Instead of adding invisible matter, MOND proposes that gravity strengthens at low speeds. Other discussions in physics include dark energy and dark matter, concepts introduced to explain certain cosmic phenomena. Some critics argue these ideas are unnecessary and that alternative explanations could exist. Scientists who challenge Einstein's theory of gravity explore possibilities such as unknown forces or particles that could refine our understanding of gravity. In science, new ideas are not disregarded. Rather, they are rigorously tested. For example, Einstein's concept of time as a fourth dimension has inspired discussions about time travel, wormholes, and Stephen Hawking's chronology protection conjecture, which suggests that traveling back in time is unlikely from a physics perspective. Ongoing experiments continue to explore whether new theories can explain gravity in ways consistent with known observations. Despite numerous alternative ideas, none have successfully replaced general relativity. Doubting and challenging established theories is a crucial part of scientific progress, leading to deeper insights into the universe. However, general relativity remains the most successful theory of gravity, consistently passing every test and explaining key phenomena such as planetary motion and light bending around massive objects. According to special relativity, time behaves differently depending on movement. This has real-world implications, especially for space travel. Since the speed of light is the fastest possible speed, interstellar travel presents a significant challenge. The famous twin paradox illustrates time dilation. If one twin remains on Earth while the other travels at high speed to a distant star and returns, the traveling twin will have aged less than their sibling. This means they have effectively traveled into the future. Time dilation is crucial for space travelers. The longer the journey, the slower time passes for them relative to people on Earth. If astronauts were to visit nearby stars where time slows significantly, they might age much slower than those on Earth. While this sounds like science fiction, it is a genuine result of relativity. For example, if humans were to send a crew to a nearby star system, the trip could take decades or even centuries by Earth's time. However, for the astronauts, the journey would feel much shorter due to time dilation. This effect also impacts technology. Computers and communication devices on spacecraft must account for time dilation to function correctly. Space travel at high speeds presents other challenges, such as prolonged isolation, cosmic radiation exposure, and psychological effects from extended periods away from Earth. Even in our daily lives, we see the effects of time dilation in GPS, Global Positioning System satellites. These satellites experience time dilation due to their movement, and if this effect were not accounted for, GPS calculations would be inaccurate. One fundamental question in physics is why time moves in only one direction. Time governs our existence, moving from the past to the present and into the future. This one-way flow of time is linked to entropy, the measure of randomness or disorder in a system. According to the second law of thermodynamics, the total entropy of an isolated system will either increase or remain constant. In simple terms, entropy naturally increases rather than decreases. Observing everyday events helps illustrate this. Imagine a deck of cards neatly arranged. If you shuffle them, they become disordered. This transition from order to disorder mirrors the arrow of time. Similar effects can be seen in phenomena like ice melting or coffee mixing into milk. Ultimately, general relativity remains one of the most successful scientific theories ever developed. It explains gravity, planetary motion, black holes, gravitational waves, and the nature of spacetime itself. While new ideas and alternative theories continue to be explored, relativity has stood the test of time, proving to be a cornerstone of modern physics.